Am I going to one more time?
1 psi.
1 psi is equal to 2.31 feet of water. And 1 foot of water is equal to 0.433 psi.
Something you might bring up right there is that it's real important when you're checking that to use the same pressure gauge or to use the same meter, because if you have a pressure gauge on your incoming and your outgoing and you use those two, the differential between those, I mean, if one's a pound or two higher and the other one's a pound or two lower and just out of calibration or whatever, you really don't care what the exact pounds is, you're after the differential. So even if your one gauge you're using is out of calibration, if you read 10 feet over here and you read 20 feet over here, you still know you got a 10-foot differential, and then we'll be accurate on there, because as you can see, 5 foot makes a heck of a difference on a chart like that.
Exactly, and Darrell brings up an excellent point. It's called gauge error, where both gauges may not be calibrated exactly alike. What I like to see is a differential pressure control that has a 1/4-inch line going into each one. You can put a little manual shutoff valve here, and you're taking the differential pressure across using the one gauge, and you get rid of that 2 different gauges deal. In fact, a lot of times on flow, you can go get a certain type of photohelic that not only gives you the reading, but actually is the flow switch functionality as well for the chiller using this. It's a little more expensive than your typical paddle flow switch, but that's another thing that, thank you for bringing that up. Again, here's a typical log sheet. And again, we have all the condenser data lumped together, the in and out temperatures, the in and out pressures, the pressure, and then you calculate the pressure difference across the condenser based on those, and you note the refrigerant temperature. You do the same for the evaporator. You can get information off the instrument panel. And again, each chiller may be customized. You can customize something like this. And then the motor, your oil sump temperatures, if you can get bearing temperatures, oil levels and site classes. You want to write down your amp draw and your voltages for each phase. Some chillers have current limiting where you can dial it in to limit it to 70% of capacity, and you want to make a note of that just for your own reference. And if you have a low pressure chiller and you have a purge unit on it, I know the train purges have the ability to track pump out time, and that's a great indicator of when you're starting to develop a leak. The more pump out time you have, the more likely, the bigger the leak. So this is all good information. We'll talk about how it plays out. Down here again is your design information that you put in there. Put it on each log sheet so you can see how your pressure drop on your water side here, your differential pressure is comparing to down here, and see if it's getting off. This just happens to be for a train screw chiller. Again, my suggestion is you can customize any log you want. Tracking the number of hours of runtime and starts is good too, but in today's newer chillers, you've got a display panel and you just go through and it gives you most of this stuff. You could even create your log sheet to follow exactly what your display shows you and put it in that way. So it's easy for, in today's world, you don't have to worry about calibrated gauges a lot of the times and calibrated sensors. It's all built into the chiller and you can just write it down. The nice thing about having it here is now someone can look at it and see trends like that. So here's an example of a performance data from the manufacturer for, it happens to be the Docking State Office building, one of the chillers there. It's a 405-ton chiller, shows the KW per ton. Gives you your entering and leaving water temperatures at design and the flow rates and the pressure drops at that flow rate. and same with the condenser, and it gives you your rated load amps at selection kW, which is the key thing you want to write down in your design. 378 amps when you're 100% loaded is what you should expect in that application. So you put that down in the bottom of that log sheet so you always can look at that and compare it to what you're actually logging. So let's start talking about some of the things that you're logging and what they're telling you. First of all, I want to talk about definitions. The first definition, and it's actually one of the most important ones, is approach temperature. Approach temperature is a difference. I'm just going to talk condenser here. It's the difference between the leaving water temperature in the condenser and the temperature of the refrigerant in the condenser. And I've got a picture that'll help put this into perspective in a little bit. But it is, again, the difference between the leaving water temperature and the refrigerant liquid temperature of that condenser or evaporator. We have a concept called lift. This defines how much work the compressor has to do, how much lift it has to work to create in the refrigerant to get the refrigeration cycle to work. Okay, it's easy to read temperatures and pictorially display temperature difference in lift. The reality is the work is done with the pressure difference, and there's only one thing, maybe one problem that may result in a difference between these two. But this lift is how hard your machine has to work. It's the difference between the refrigerant, the condenser temperature and or pressure, and the evaporator refrigerant temperature and pressure. I want to spend a little bit of time on this chart because this puts it all in perspective. This is a typical water-cooled chiller. You've got 85 degree coming out of the cooling tower entering the condenser. It absorbs the heat out of the machine and leaves the condenser at 95 degrees. Goes back to the cooling tower. Well, it happens to be that you have a condenser approach temperature of 7 degrees, which puts your condenser refrigerant temperature at 102. Conversely, on the evaporator side, you've got building water coming back to the chiller at 55. You're cooling it down to 45 and sending it out to the building. So you got a 10 degree delta T on the chiller loop side. And your evaporator approach temperature is 7 degrees, which puts your evaporator refrigerant temperature at 38 degrees. Now, the difference between the evaporator refrigerant temperature and the condenser refrigerant temperature defines your lift in degrees Fahrenheit. So this chiller, this compressor has to create a 64 degree Fahrenheit lift to do work. Now, in today's world of high efficiency chillers, how are they tackling this a lot of the times? They're reducing the approach temperature. They're throwing more tubes into tube bundles or going to plate frame heat exchangers or other strategies to reduce this. Old chillers had 7 to 10 degrees approach temperature. The ones today are 2 to 4 degrees. So if you can lower that 3 degrees and do the same on the evaporator 3 degrees, your lift becomes 58. The compressor doesn't have to work as hard. You save energy. Now, why do you care about this and why is it worthwhile logging it and acting on it quickly? And a lot of people say, well, if it shuts down, then I'll call somebody. Well, here's why. For every 1 degree of lift that you increase, it's going to cost you about 1.5% in your efficiency. Now, I'll tell you, I just ran some very rough, quick numbers on a 400-ton chiller, and a 400-ton chiller will more than likely cost you on a typical office building in this part of the country, about an electric bill, about $48,000 to $100,000 a year to run. So that means, with your savings, 1%, if you're 1 degree up, 1.5% is going to be $720 to $1,500. that year that you just said, well, I'll just wait, you know. It's worth looking at in a timely manner and not waiting. So, again, evaporator approach temperatures, these are rules of thumb for some train chillers. Some of the older ones, depending on the number of passes, had varying evaporator approach temperatures. You don't see many one-pass machines anymore. 2 passes are the most common. And where there were 7 to 10 and 8 to 11 back then, now they're anywhere from 1.5 to 4. One of the things you want to do, you're logging the amp draws, and down at the bottom of the log sheet is the design, what was it, 378 amps at 100%? Well, maybe you're running at 200 amps. You can take 200 amps over the 378 times 100, and that'll give you your percent motor load. That's how loaded electrically the machine is, what it's running. You may find you're at 60% load. You can do a quickie calculation there. So if you're at 60% load here and you got a 10-degree delta T on design, maybe you're just doing a 6-degree delta T and everything checks. Okay? So now I'm getting into the, don't just write down numbers, what can you do with them, okay? You can also calculate your kW consumption. You take the volts and amps times 1.73 times the power factor, divide by 1,000, and you get the actual kW that you're using. And I put in some typical motor power factors. These are for train centrifugals, but they would be valid for most compressor motors. Again, power factor is electrical efficiency. You know, a lot of equipment has mechanical efficiencies. Power factor is electrical efficiency. What else can you do? When you have your 3 voltages by legs, you can put them into this equation and calculate out your average and your percent of voltage imbalance. You can use the same equation if your display gives you amps by phase too. You can use the same equation to plug in all 3 phases of amps, come up with an average and your percent of imbalance. So why is that important? It can actually result in one leg running quite a bit warmer than another one, causing potential problems on your machine. And voltage imbalance, there's a leverage with voltage imbalance that affects current imbalance quite a bit. At full load, 1% voltage imbalance will create an 8% current imbalance. And if you have one leg running a lot hotter than the others, it can cause you to trip on that one overload or other problems that you trip out on, motor winding temperature, etc. And it may just be something simple on that voltage imbalance. If you identify it in a log, it may be something simple like the connections on your starter just need to get tightened down, or a wire is skinned or something. You know, it could be as simple as that. It could be that the power supply coming in is just not equal from your power company. Again, I guess I jumped the gun here. Possible causes of voltage imbalance, incoming power problem, your starter, your contactors, wiring. This is one of the reasons you have starter maintenance done on a chiller inspection. Check the contactors for pitting and tighten all the terminals down and go from there. Check the wiring.